We talked in previous videos about factors that are important when we are predicting products and radical reactions. One thing that we talk about is the type of hydrogen that we are extracting in the first propagation step. And here, remember, we talk about bond dissociation energies, in that the easier to break the bond, the smaller the bond dissociation energy, that leads to the formation of the more stable radical. So in general, it's much easier to extract a benzylic hydrogen in that than allylic. And then we have tertiary. So this is the east to break, right? And in that direction, the secondary, primary, metal, and so on. One factor that we talk about also when you are predicting products is, I'm going to, I know that Carl, the other wasn't so bright, we need to take into account the geometry of the radical. And remember that this is trigonoplanar, and that if you are creating chiral centers, you will form two enantiomers because the attack can be from either side of the plane when you have the radical. So now that's one consideration. The third consideration that I want to make is the halide itself. So in general, you have fluorine, chlorine, bromine, and iodide for one thing. And when you're doing radical reactions, you don't use fluorine because it's too reactive. Reactions are explosive, and also you get just a ton of products different. But it's very difficult to manage that experimentally. We don't use either iodide because it's not reactive and it's not favorable when thermodynamically speaking. So the two reactions that we use the most is the chlorination and the bromination. Of that, there are differences. Chlorine is more reactive. It makes reacts faster, but it's less selective. So here we typically form many products. Bromine, however, is less reactive and more selective. Those things go together. So how practical this is, why do we want to use bromination or chlorination? Then depends of if we want to get one specific product. Then in many cases, bromination is preferred, but you can use chlorination, which is faster, in case of, say, that you have this molecule right here, so metal cyclohexane. Here, the preferred position will be this one, abstracting this hydrogen, because it's tertiary, and is the main product, essentially. That's primary, and all the other secondary. So that's somewhat clean reaction in the term in regards to chlorination. So you can use it, and it's faster. But there are cases, like the molecule that I drew before, in which you may have very different. So this is tertiary, and you have secondary, primaries. You may have a lot of products in that case, so it's not practical. So for those purposes, we may prefer to use bromination. And there are also other specific reagents that, in the case of, remember when we talk about this type of hydrogens, well, when we have allylic and a benzylic, we use a reagent called n-bromosuccinimide. And n-bromosuccinimide is important, and we are going to be talking that in another video. Why do we use for allylic and benzylic bromination, particularly in allylic? Why is it so important to use NBS? Well, we prefer that over using bromine and, say, light, right? Okay, so we're going to be talking about that a little later. But remember, these are factors that we need to consider. So the type of hydrogen that you're abstracting, the geometry of the radical to be able to predict whether you're forming an enantiomers or not at a given center, and what is the halide? So we're not using fluorine, we're not using iodine, we're just using chlorine and bromine for those reactions.